To hear my name from a Greek guy, it's always correct. Um, Thank you, everybody. Thank you for the very kind invitation and for the great couple of days that we're spending here in Tallinn with the exhibition, but more than anything, with the people that we have gathered here. Thanks also, Rachel, for a great, where is Rachel? She disappeared. For a great introduction on liquid cities, on cities that I am also interested in the sense of non-rigid cities, cities that go beyond the functionalist belief that things should stay there forever, and sustainability is related with things that they can protect us, and they can be protected by the environment, and they need to stay there forever. So I will be talking about this idea of responsive cities, starting with more bottom-up approaches of the scale of the materials. That's why I want to see how material can be augmented in different ways, and that is why I'm going to be showing a series of different projects so that we can design performance, so that we can program those materials in order to perform. So the Anthropocene is a word that we have been listening and talking about the last couple of days, especially here. And sorry, I am here, okay. Yes. So the Anthropocene is basically directly connected to my understanding with growth. And growth, of course, in many aspects. Growth of economy or profit. There is an excellent work by Donna Haraway explaining how the Anthropocene is basically more capitalocene than Anthropocene. But it's connected with that growth, and it is connected with the mass production of products, the mass production of services, of resources, and of course it is related with our mass consumption societies. And in its essence, that growth, which it is considered to be emerging by the second industrial revolution and maturing during the information age and the digital revolution, it has been ruled by assumptions of standardized people having standardized needs and, of course, being and inhabiting standardized environments. And that idea of standardization and that functionalist belief of standardization, it resulted in this kind of environments that you see on the screen. No? They're environments that they are static, environments that they are standardized, environments that they are repetitive. So our contemporary cities and buildings, they are based on Cartesian grids, they are based on repetition, and they are based on standard forms. And if we think that we are at an era of accelerating technological change, we are at an era of ethnic diversity, of techno-social systems, we are at an era of continuous changing social, economical, or environmental needs, then we need to understand that architecture and urbanism, it should give a step towards a more dynamic and more responsive performances. It cannot be that static, standard form that we have been building for the last years. So buildings and cities will need to have new interfaces in order to communicate with the environment, but they will also need embedded systems of performance that do not rely on existing infrastructure, existing urban or building infrastructure. And that is probably where we all meet, where the work that we all do, the ones that we have been presenting and meeting those days. This is the moment of questioning the standardization and the mass. And that moment of Anthropocene is really the one that I believe it's the most interesting one, the most contemporary form of it. And there is no doubt, of course, that the advances of interaction and production technologies in combination with advances in material sciences, bioengineers, synthetic biology, we have been seeing all this work, especially yesterday in the talk of many of the friends here, they start to impact architecture in unseen ways. And we are seeing wearables that they can allow us to see things that they are not there, virtual and augmented reality, overlapping of physical with the digital space. We see building skins that they are starting to move, to interact, to adapt, to grow. We see programmed and programmable materials, and we even see the possibility of self-fabricating our shelters, our houses, our architecture, and our environment by downloading files on the internet that they are open source and are being able to manipulate it by anybody that is not really expert on that. So at a moment of a novel intersection and cross between digital and physical, between bits and atoms, between fluid and statics, matter is becoming expanded. Matter is becoming ubiquitous. Matter can be found everywhere, in the physical reality, in the digital reality. Matter can adapt, it can self-repair, it can be programmed, and eventually it can be built or manipulated or processed by anybody that is connected to the internet or to an interface. And allow me to see a series of examples of how can we augment that ubiquitous matter and how we can process that matter to enhance its properties so that we can program a series of performance, or we can predict and use part of that properties of the matter into our built environment. That is a warning that it's not going to be as bio as it has been, what we've seen until now. But still very much into this idea of nano, into this idea that small is the new big. So the first project I will be showing is the breathing skin. It's a project that is working with hydromorph, expanding hydromorphs, hydrogels. I don't know if you are all aware with those materials, but they are basically polymeric elastic materials that they have hydrophilic properties, which means that they are able to absorb water in quantities that they are much bigger than their volume or than their size, and they can retain that water into their nanostructure. And then when the environment it is in such conditions, such as, for example, high temperature, that water can evaporate. And by working with that cycle of absorbing and evaporating water, we can start thinking of how we can create much more passive ventilation or cooling systems for our architecture and our built environments, that they are alternative to the artificial cooling that we're using today. So if you can play the video, please. So that is a very simple video of showing the performance of that material, designed in a specific way so that we can create a cell that it is a composite and that encapsulates that material with textile, with elastic fabric. And then following a library of experiments, if you can keep on playing that video, following these experiments that we have been doing in the different design geometries and patterns, we have seen that there are optimum designs and scales of that cell, even orientation, so where we place those cells according to the different contexts and the different environments. The final skill that we are proposing, it consists on different cells whose geometry is able to transform, and it is able to open and close so that we can allow ventilation on one hand to happen, but on the other hand, taking advantage of the high temperatures of outside, it is able to evaporate that water and create a cooling effect into the interior. So different type of textiles, different type of geometries and colors have been tested to evaluate the composite performance and to understand what is the relation between the design of it and the specific context where it would be appropriate to, let's say, apply to. And taking into account the lack of water in a lot of climates around the world, the design of the system is based on a tensile conical structure, so that it is actually a fog net that it is able to absorb fog and then distribute that moisture along the whole surface. So the system, it takes advantage of this natural cyclical operation, and it does not require any external energy or any cost-effective system to maintain it and to operate it. And it can be, of course, be an interesting solution to places where there is a water shortage, but also it is interesting because it has been applied in a design that it is also tensile and pliable, so adequate for urban spaces or public spaces in areas where climate is extremely hot. To evaluate and understand that performance of both the material and the system that we were creating, we have been using different computational techniques, CFD wind analysis, but also solar radiation analysis in order to see in which part of that structure the cells would be applied, no? In what density, in what scale, and in what exact position. And those are not very visible, but those are some diagrams that they have been showing. We have been evaluating our solution in different environments, and we have seen that we could eventually drop the temperature by 5 degrees. 5 degrees, if we translate that into the use of air conditioning, it could even be 20 or 22% of use of artificial cooling. And not only it allows us to save in cooling, and therefore in energy, and therefore in CO2 emissions, and therefore in costs and economy, but it also could be eventually an alternative solution to artificial cooling, so without using any of external energy resource. My next approach and project is here because I want to, more than anything, debate on what I was discussing a bit in the beginning, which is the outcome of our mass consumption, our mass production model. So our current model in cities is one that we are basically produced very far away from where we consume. And then we transport those mass-produced products, and we consume them like very far away from where they are produced. We spend money, we spend energy to transport them into the logistics that surrounds that operation. And then not only that, but when it comes to our hands, our houses, and our everyday lives, and we consume them, then we are also creating waste. That waste is also being transported. It's also being moved from the cities. So in a way, again, we are spending energy and we are spending money into that model of non-sustainable production, that it is basically the production model of the second industrial revolution. So I am showing that project because it searches on possibilities of using waste as the future material, so that everything that we consume, it actually stays here with us, and we can recycle them and we can reuse them. And that material has been engineered, it has been used with additive manufacturing techniques, we 3D print it, and we used computational design for creating a kind of a bioplastic material that it is based on. Can you play the video? It is based on waste of our everyday life. So we're using the waste, and the organic waste that we're using, it's basically coffee and orange skin waste. And such waste gives different properties to the new composite. And that is interesting because according to the properties of coffee or orange peels, which is a bit the two case studies that we have been testing here, the properties are different. Coffee is hydrophobic, which means that it can be placed and used in areas where we need that this is protected by water or rain or outdoor conditions. Orange skin is enhancing structural properties, which mean that it can be placed and it can be used in areas where we need to enhance our structural performance of our three-dimensional structures. And it is also interesting the fact that by depositing that material where exactly we need it, our computational design is able to, in a way, show us what should be the initial form in order to achieve a final one that it is after drying, deformed, and it's being creating I lost the video? Okay. It is somehow creating a new performative prototype where the form is much more different than the one that we initiated. So, talking about that future materials and which will be those materials, I am also very interested and I am very, very fascinated with the very recently discovered material of graphene. I guess you already know about it, but if you don't, graphene is a material that has extraordinary properties. It is a material that can be, it is stronger than the strongest steel. It is a material that is conductive, high conductive, but not only conductive, it is also like a supercapacitor, which means that it is able to store energy, so it's able to collect, distribute, store energy, and eventually it is a monolayer lattice in its nanoscale, which also means that it is a very thin layer that could be applied into different materials. And of course, it could even get to be transparent. So in this project, we have been, can you play the video? Yeah. We have been working with this, with applying graphene into silicon and soft textile surfaces in order to try to see how we can activate a surface just by bending. So the bending could basically happen by natural forces, such as, for instance, the wind, but it can also happen by users that they can directly interact with those dynamic systems. So it's not like we leave nature to decide on how architecture could be formed, but it could be really a kind of a more open interaction among built environments, among environments and the people. So that scheme that is being able to operate, which means switch on and off by wind or by stretching, is able to collect energy by the sun. Graphene is being used to create high-efficient solar panels because, as I said, it's a supercapacitor. I mean, we can generate the energy, we can store it, and then the same skin of the building can intelligently distribute that energy into the building. So, in a way, we have a kind of an embedded intelligence, and what I always like to say is that this is a very, very initial, it's the first project that we did in graphene, but our goal has been to try to see how we can create physical interfaces, not digital ones, but interfaces that they could be embedded into the materiality of our built environment. That is a work that we are developing in collaboration with the Italian Institute of Technology, the Smart Materials Group, and this is a small prototype, or you can see how this interaction can happen. At the moment, it's only light on and off, but at the moment that you have this operation, you can activate or deactivate different inputs and outputs. Okay, so continuing with the idea of creating embedded intelligence and architectural elements that have this embedded intelligence onto their materiality, and continuing, of course, with my obsession with graphene, that is another project that we have been developing a few months back, again in collaboration with the IIT, and I will ask you if you please take pictures, just don't take pictures of that. But that is a work that it is under development. If you can play the video, thank you. It is under development, and what we are working here is to test a series of programmable patterns for mixing two materials, for mixing traditional materials such as clay or concrete with graphene nanoplatelets. So graphene is able to, as I said, to conduct electricity and, of course, to also become a thermal conductor. And we have been trying to create a composite, a brick, that it is a functionally graded material brick where we can regulate thermal conductivity and we can therefore regulate heating in the interior of the building. So we use 3D printing for creating that functionally graded material, and in the form of a wall, we can see that we can decide where we can place the different mixes of percentage of graphene with clay or with either concrete. So in the bottom of the wall, in that first prototype that you see, we have more density of graphene, which means that the thermal conductivity is higher, which means that that part of the wall is warmer. And then as you go upper, that becomes colder, that becomes less warm, and that becomes, of course, less density of the conductive material that we need. So the different performances are related with different mixes that can be customized, and can be customized according to the design, and it can be customized according to the need of the interior microclimates. And the different customized mixes, they can create a homogeneous surface that it performs differently along the same surface. This is one of the final pieces, the first and final pieces at the moment we printed to achieve this functionally differentiation and to produce the range of heat transfer intensities. Passing to another project, this is basically here to honor the title of the symposium. I'm kidding. But it's a project that we have been developing, trying to understand how biology and natural growth could give back to architecture or could be combined with architecture. And we have been working with Physarum and slime mold, as I guess Heather you will be talking in a while in much more depth than I will. But what we have been interested in doing with that material is to apply it into our human environments and to create not extracting the logics and trying to apply them into architecture, as many great projects have done. So we know that Physarum is great in the way that it grows. We know that it creates this kind of optimum network connections. But what we wanted to do is to treat Physarum as if it was a kind of a plant, in the sense that we wanted to embed it into an architecture that would require that architecture to be grown by people. And that architecture would give back to the people in the sense that it could be customized either in color or either in density and transparency based on where do you place the food as user of that, or how much food do you place there. So this is a kind of a screen that we have been testing in a grids, and we have been putting like different food and in different positions so that we can control like the density of a panel. That is a separation panel. It can be a wall. It can be a facade composite panel. And then according to where the Physarum grows, it creates different densities and transparencies, but it can also create different colors. On that. This is installation that the students have been mounting for a couple of weeks, but we have also created a kind of an automated machine that was placing the food where we really needed to do that. That is important, that slime mold can also grow like pretty fast. So in 7 hours, you could have like different patterns created by you as a user. Finally, and that is the last project I'm going to show, which is the project that I want to invite you all to visit. We want to invite you all to visit. We're a great team coming from Barcelona and IAAC. Maria Kupchova and Raimund Krenmuller have been living here for the last 10 days to set it up and have been working on that like the whole summer moment. But what it is interesting about that project is that it explores an alternative solution to managing the extensive plastic waste in our marine environments. And that project is trying to combine a very significant problematic of our environment technological advancements in terms of what kind of machines we can create that they can help us to deal with that microplastic, and biological advancements that they can also help us to deal with that microplastic, no? And the studies that we have been doing is basically how we can use biology and bacteria to put this microplastic together, to biocement it, quote to quote, in bigger pieces. Because the problem of microplastic is that it is such small pieces that you cannot really detect it, you cannot collect it, and since you cannot detect it and collect it, you can hardly even calculate what's the impact of that microplastic in our marine environments, in our food, and et cetera, et cetera. So, biology on the one hand to bring this plastic together, but also what we have been thinking of is that we are interested to create this kind of new artificial species, this new artificial animal, that it is an aerial robot, it is a mini nano robot, that it is able to fly, but it is also able to dip into the water and to collect that plastic. So the whole digestive and intestine system of how this mini robot works has been created by following the cycles of filtering microplastic, entering bacteria so that this microplastic could be collected into bigger pieces, and eventually, once that plastic is collected, it could be deposited so that it could create a material that it could be reused. That material can create other additional mini robots, or it can also create a material for us to 3D print in our houses or for any other purposes that can even scale up. So it is a kind of a artificial system. Here you can see, I thought we were in that slide, here you can see the intestines and that digestive system that I was talking about. And that bioartificial system is creating interaction between natural and artificial system in the Baltic Sea. And can you play the video? Okay, so that is the video of the installation that I guess you have also seen yesterday in the opening. We first extract the contained microplastic from the marine environment and then pass it through that complex digestive system of this weird animal that you will see in a while in the screen. We are able to filter it, collect it, and create material to reuse again. What is also fascinating is the fact that technology can really allow us to start creating that performative species based on what we want them to do, but also, and that was the discussion a bit on the morning, also allow them to learn from that condition. So artificial intelligence and learning of those species could start create a kind of a merge between what technology can bring and what this new contemporary Anthropocene can bring into architecture and urban environments. Okay. So just to sum up, what is clear is that we are not anymore facing, or we're not anymore in front of a mother nature, the way that we have it in our mind, or the way that ancient and religions are brought to our mind. But we're in front of a nature that it is a more trans nature or a more techno nature or a post-human nature. And that nature is not only behavioral and operational, but it is also programmable. And it is able to be manipulated. And it is imperfect. And it is what in many circles is known as dark nature or dark ecology or even black ecology. And in that dark ecology or dark nature, what we see as a significant difference from the models that we have been seeing until now is this merge of human and technological agents. And in that Anthropocene or Capitalocene era, we've seen that buildings are becoming computers. They were once the size of a building. The first ENIAC was a building in itself. Now buildings are becoming computers. Matter becomes programmable. Biology is being hacked. Ecology and nature becomes dark. And architecture in its turn, it becomes customized. It becomes interactive, technologically integrated and evolutional. And I think that the challenge of us designers is really how we can contribute into that interactive, customized, and technologically integrated architecture. Thank you very much.